13 billion years ago, there was nothing. No light, no darkness, no space to hold either. Then, in one incomprehensible instant, everything exploded into existence. The universe screamed its first breath, hurling matter and energy across an infinite void that didn't exist a heartbeat before. You think you know creation stories? Forget them. This wasn't gentle, this wasn't planned, this was violence on a scale that would shatter your mind. The temperature at that first moment? 100 billion degrees. Hot enough to melt the concept of matter itself. For the first fraction of a second, a time so brief it makes lightning look lazy, fundamental forces battled for dominance in a cosmic war that would determine whether anything could ever exist at all. Protons and neutrons crashed together like bullets in a furnace. Electrons spiraled through space-time that was still deciding what it wanted to be. The universe expanded faster than light itself, growing from smaller than an atom to larger than a grapefruit in less time than it takes your neurons to fire. This is the story they don't teach you, the brutal, beautiful birth of everything you've ever known. What I'm about to reveal comes from cosmic records written in starlight itself, evidence so overwhelming that it would make the ancient Norse tremble at their vision of Ginnunga Gap, the Great Void. The Egyptians called it Nun, the primordial waters. The Hindus spoke of the golden egg floating in darkness. They all sensed something. They just didn't know how terrifyingly magnificent the truth really was. But here's what no scroll has ever captured, what no mythology dared imagine. You are made from the ashes of that cosmic violence. Every atom in your body was forged in the nuclear hearts of dying stars, then scattered across the galaxy in explosions so powerful they outshone entire solar systems. Subscribe now, because the story you're about to hear will change how you see every breath you take, every beat of your heart. 4.5 billion years ago, in a spiral arm of a galaxy we now call the Milky Way, something extraordinary was happening. A massive star, 20 times larger than our sun, was dying. Picture this giant in its final moments. For millions of years, it had burned hydrogen into helium, helium into carbon, carbon into iron. Each fusion reaction had fought against the star's own crushing gravity, but iron doesn't burn. Iron kills stars. The core collapsed in half a second to destroy something 20 times the size of our sun. The shock wave that followed tore through 10 billion tons of stellar material, flinging it across space at 30,000 miles per second. In that explosion, that supernova, every element heavier than iron was born. Gold, silver, uranium, the calcium in your bones, the iron in your blood, all of it forged in the death scream of a giant star. The shock wave rippled outward through space, carrying with it a gravitational whisper that would change everything. Nearby, a massive cloud of gas and dust, mostly hydrogen left over from the universe's violent birth, felt that whisper and began to stir. Gravity is patient. Gravity is relentless. Grain by grain, particle by particle, the cloud began to collapse inward. At first, the movement was gentle, almost imperceptible. But as more matter gathered, the pull grew stronger. The cloud spun faster. The center grew hotter. For 100,000 years, this cosmic dance continued, temperature rising, pressure building. The core of this collapsing cloud reached 15 million degrees Celsius. And then, like striking a match in a powder keg, nuclear fusion ignited. Our sun was born in fire. But the sun wasn't alone. The remaining gas and dust formed a disk around the newborn star, a disk that would birth worlds. Inside this disk, particles of rock and ice began their own gravitational ballet. Tiny grains stuck together, small rocks crashed into each other and grew larger. Planetesimals the size of asteroids hunted each other through the void, colliding and merging in violent embraces that would have made the gods weep. For 50 million years, this chaos reigned, and from it, a small, rocky world began to take shape in the third orbit from the sun. The infant Earth was nothing like the blue marble you know. This was a hell world, a molten ball of rock covered in magma oceans that glowed like the devil's forge. The atmosphere was poison, methane, ammonia, and hydrogen sulfide thick enough to choke giants. Volcanic eruptions that make Krakatoa look like a crocker split the surface every few minutes. Comets and asteroids rained down like bullets from heaven, each impact adding more violence to an already chaotic world. The planet spun wildly. A day lasted only 6 hours. There were no seasons because there was barely a tilt to the axis. The moon didn't exist yet. The tides were gentle, almost non-existent. The surface temperature averaged 1200 degrees Celsius, hot enough to melt copper, hot enough to make granite flow like water. But the real violence was yet to come. Somewhere in the outer solar system, a Mars-sized planet called Theia was wandering. For millions of years, it had carved out its own orbit, minding its own business, cooling and solidifying just like Earth. But gravity has no mercy for wanderers. Theia's orbit became unstable. Maybe Jupiter's massive gravity nudged it. Maybe a passing asteroid cluster knocked it off course. The exact cause is lost to time. What matters is the result. Theia was heading straight for Earth at 25,000 miles per hour. The impact lasted 24 minutes that rewrote the laws of geology and gave birth to the moon. When Theia struck, it hit at a glancing angle, like a cosmic sledgehammer striking a cosmic anvil. The energy released was equivalent to 40 trillion nuclear bombs detonating simultaneously. Half of Earth's crust was vaporized instantly. The other half was flung into space, along with most of Theia's mass. The remaining molten debris formed a ring around Earth, a ring so hot it glowed like a second sun. Over millions of years, this ring of molten rock would slowly condense and cool, eventually becoming the moon we see today. But the Earth that survived the collision was transformed. The impact had knocked the planet's axis into a 23-degree tilt, giving birth to seasons. It had lengthened the day to nearly 24 hours. Most importantly, it had created a massive moon that would pull at Earth's newly formed oceans with gravitational forces that make today's tides look gentle. The early moon was 3 times closer to Earth than it is now. Tides rose and fell by 300 feet twice a day. Imagine waves taller than skyscrapers rolling across empty continents every 12 hours. The very surface of the planet pulsed like a heartbeat. Steam rose from the cooling magma seas in columns that reached the edge of space. Lightning cracked across skies thick with volcanic ash and water vapor. Thunder echoed across empty continents where no ear existed to hear it. For the first time in its violent history, Earth began to rain. It rained for 2 million years. The water didn't come from the sky at first, it came from the rocks themselves. Every volcanic eruption released water vapor that had been locked in Earth's minerals since the planet's formation. Every comet that struck the surface added its own contribution of cosmic ice. Every asteroid brought frozen water from the outer solar system. The rain was scalding at first, turning to steam before it could reach the surface. But slowly, as the planet cooled, droplets began to survive the journey. They struck the hardening lava with a hiss that could be heard across continents. They pooled in the low places between volcanic ridges. They began to fill the first ocean basins. By 4 billion years ago, Earth had transformed from a hell world into something that almost resembled the planet we know. Almost. The atmosphere was still poisonous to anything we would recognize as life. The oceans were hot and acidic. The continents were barren expanses of black volcanic rock. No sound existed except the crash of waves against empty shores and the rumble of volcanoes building tomorrow's mountains. But deep beneath those hostile waves, something was stirring. Something that would change everything. In the crushing darkness of the ocean floor, where volcanic vents split the Earth's crust like infected wounds, superheated water
hot enough to dissolve flesh from bone, erupted from these underwater geysers, carrying with it a toxic cocktail of hydrogen sulfide, methane, and dissolved metals that would kill any modern life form in seconds.
This was where life chose to begin. Not in some peaceful tidal pool warmed by gentle sunlight, not in a crystal-clear mountain stream. In the most hostile environment Earth had ever created. Hotter than boiling water, more acidic than battery acid, under pressure that would crush a human body like an empty can. The first spark happened around a hydrothermal vent in what we now call the Pacific Ocean, though no continents existed to name it. Picture a chimney of black rock 50 feet tall, belching mineral-rich water at 400 degrees Celsius. Around its base, yellow and orange bacterial mats swayed in currents that carried the smell of rotten eggs and the taste of metal. Inside those mats, something unprecedented was occurring. Simple chemicals were arranging themselves into complex patterns. Carbon chains were linking with phosphorus and sulfur in combinations that had never existed before. Amino acids, the building blocks of proteins, were spontaneously forming from the primordial soup. But the real miracle wasn't the chemistry, it was what happened next. Some of these molecular chains developed a property that would define life for the next 4 billion years. They could make copies of themselves. The first self-replicating molecule was probably RNA, ribonucleic acid. Simpler than DNA, but capable of storing information and catalyzing chemical reactions. These early RNA molecules floated through the hot, mineral-rich water like microscopic ghosts, each one carrying the potential to change the world. Most of them failed. In the savage chemistry of the early ocean, complex molecules faced 1,000 ways to die. Heat could break them apart, acid could dissolve them, free radicals could shred them at the atomic level. For every RNA molecule that survived long enough to replicate, 1 million others fell apart in the hostile soup. But some survived, and those survivors changed everything. The ones that survived weren't just lucky, they were better. Faster at replicating, more resistant to heat, better at gathering resources. In the world's first evolutionary arms race, success meant out-reproducing your neighbors before the environment could kill you both. For 500 million years, these molecular gladiators battled for dominance in Earth's underwater coliseums. The winners developed protective membranes, the first cell walls. They learned to harvest energy from chemical reactions, the first metabolism. They developed the ability to sense their environment and move toward food sources, the first nervous systems, if you can call them that. By 3.5 billion years ago, the first true cells had emerged. They were still impossibly primitive by modern standards, just bags of chemicals with the ability to eat, grow, and divide. But they were alive in every sense that matters. They consumed resources, they reproduced, they evolved. And they were about to commit genocide on a planetary scale. The early Earth's atmosphere contained almost no oxygen. What little existed was immediately consumed by iron dissolved in the oceans, creating rusty layers that we can still see in rocks today. The first life forms didn't just tolerate this oxygen-free world, they required it. Oxygen was poison to them, as deadly as cyanide is to us. But evolution doesn't care about comfort zones. Around 3.2 billion years ago, a new type of bacteria appeared that would make oxygen obsolete seem quaint. These were cyanobacteria, blue-green algae that had developed the most revolutionary technology in Earth's history: photosynthesis. For the first time, living things could harvest energy directly from the sun. Instead of depending on the limited chemical energy available around volcanic vents, these new bacteria could tap into the massive power source that had been streaming down from the sun for billions of years. There was just one side effect. Photosynthesis produced oxygen as waste. At first, this wasn't a problem. The early cyanobacteria were few in number, and the oxygen they produced was immediately absorbed by iron and other chemicals in the ocean. But cyanobacteria had a significant advantage over their competitors: unlimited energy from the sun. They multiplied exponentially. Bacterial mats spread across shallow seas like green carpets of death. Every individual bacterium was microscopic, but together they formed structures called stromatolites, layered domes of bacterial communities that grew like coral reefs in the ancient oceans. Some of these stromatolites grew to be several feet tall and hundreds of feet across.
You can still see them today in places like Shark Bay, Australia, living remnants of Earth's first great civilization. They look harmless, even beautiful, rounded domes of rock and shallow, clear water. But these innocent-looking structures were the factories that poisoned a planet. For 800 million years, cyanobacteria pumped oxygen into Earth's atmosphere. At first, the change was invisible. All the oxygen was absorbed by a dissolved iron, creating the banded iron formations that provide most of the world's iron ore today. But eventually, around 2.4 billion years ago, all the iron was used up. Oxygen began to accumulate in the atmosphere for the first time. The effect was immediate and catastrophic. Oxygen was toxic to nearly every life form that had evolved during Earth's first 2 billion years. It reacted with their cellular machinery like molecular acid, breaking apart the very molecules they needed to survive. The Great Oxidation Event had begun, Earth's first mass extinction. Across the planet, bacterial communities that had thrived for billions of years began to die. Entire ecosystems collapsed as oxygen levels rose from virtually zero to dangerous concentrations. The anaerobic organisms that had ruled Earth since life began were forced into hiding, deep underground, in oxygen-free environments where they remain today. But evolution is about survival, not fairness. Some organisms developed new cellular machinery that could not only tolerate oxygen, but use it. These aerobic bacteria could extract 20 times more energy from their food than their anaerobic ancestors. They grew larger, they grew faster, they grew more complex. The first eukaryotic cells, cells with nuclei, appeared around 2 billion years ago. These were evolutionary titans compared to their bacterial predecessors. Where bacteria were simple bags of chemicals, eukaryotic cells had internal structures, nuclei to protect their DNA, mitochondria to generate energy, and eventually chloroplasts to harvest sunlight. Most remarkably, these early eukaryotes began to do something no life form had ever done before. They started eating each other. Predation changed everything. For the first time, being bigger was an advantage. Being faster was an advantage. Being able to sense and avoid danger was an advantage. The evolutionary arms race that had been fought with chemistry for billions of years suddenly became a war of size, speed, and intelligence. By 1.5 billion years ago, some eukaryotic cells had grown large enough to be visible to the naked eye, giants in the microscopic world. They developed specialized structures for movement, whip-like flagella that could propel them through water, hair-like cilia that could sweep food into their mouths. But the real breakthrough came when some of these cells stopped living alone. The first multicellular organisms appeared around 1 billion years ago. At first, they were just clusters of identical cells stuck together, barely more complex than a bacterial mat. But even this simple cooperation offered advantages. Cells on the outside of the cluster could specialize in protection and movement. Cells on the inside could focus on digestion and reproduction. Specialization led to complexity.
Some clusters developed cells that could only perform one function, but performed it exceptionally well. Muscle cells that could contract with tremendous force. Nerve cells that could carry electrical signals across the organism's body. Digestive cells that could break down food more efficiently than any single-celled organism. By 600 million years ago, Earth's oceans were home to creatures that would have been recognizable as animals. The first multicellular life forms with tissues, organs, and primitive nervous systems. They were still soft-bodied, still microscopic by modern standards, but they represented a revolution in biological organization. These early animals faced a world that was finally becoming hospitable to complex life. Oxygen levels had stabilized at concentrations that could support large, active organisms. The ozone layer, formed by oxygen high in the atmosphere, was beginning to shield the surface from deadly ultraviolet radiation. Ocean chemistry had shifted from the toxic soup of Earth's youth to something approaching the life-supporting seas we know today. But the greatest changes were yet to come. Deep beneath the ocean's surface, tectonic forces that had been reshaping the planet for billions of years were building to a crescendo. The first supercontinents were beginning to form as smaller landmasses crashed together like slow-motion bullets. Mountain ranges taller than the Himalayas thrust skyward from collision zones where entire continents ground against each other.
These geological upheavals triggered climate changes that made the Great Oxidation Event look gentle. Ice ages locked the planet in frozen silence for millions of years at a time. Volcanic eruptions large enough to cover entire continents with lava released gases that turned the atmosphere into a suffocating blanket. Through it all, life endured. It adapted. It evolved. And it was preparing for the greatest explosion of creativity in Earth's history. But first, it would have to survive the most extreme climate catastrophe the planet had ever seen. A deep freeze so severe that ice covered the oceans from pole to pole, turning Earth into a giant snowball spinning through space. The survivors of Snowball Earth would emerge into a world transformed, ready to experiment with body plans and survival strategies so radical they would make the dinosaurs look conservative. The stage was set for the Cambrian explosion, the biological Big Bang that would scatter complex life across the planet like shrapnel from a cosmic bomb. But that's a story for another day. Right now, somewhere in your body, ancient bacteria that survived the Great Oxidation Event are still working in your cells, converting oxygen into energy the same way they did 2 billion years ago. You are not just descendant from those early survivors. You are a walking ecosystem of them, a living reminder that life doesn't just adapt to change. Life becomes change. The planet was suffocating. For 10 million years, Earth had been locked in ice so thick that even the equatorial oceans froze solid. Snowball Earth, a frozen hell where temperatures dropped to minus 50 degrees Celsius at the warmest spots. No liquid water anywhere on the surface. No photosynthesis. No food chains. Just ice stretching from pole to pole like a cosmic morgue. But beneath that ice, something extraordinary was happening. Volcanic vents continued to pump heat and chemicals into the dark ocean beneath the frozen shell. And in that darkness, life was doing what it does best, finding a way to survive the impossible. When the ice finally cracked around 635 million years ago, it happened fast, catastrophically fast. The same greenhouse gases that had been building up under the ice for millions of years suddenly turned Earth into a furnace. Average temperatures shot up 40 degrees Celsius in less than 1,000 years. The survivors that crawled out of that thaw were different, tougher, more complex, ready to explode across a planet that had never seen anything like them before. What happened next makes every other moment in Earth's history look like a warm-up act.
The Cambrian explosion wasn't gradual, it wasn't gentle. In 25 million years, a geological eye blink, life went from simple, soft-bodied creatures hiding in the ocean depths to an alien menagerie of armored monsters that would give your nightmares. Trilobites scuttled across the seafloor on dozens of jointed legs, their compound eyes containing more than 15,000 individual lenses, each one capable of detecting the polarization of light. These weren't simple creatures fumbling around in the dark. These were sophisticated predators with better vision than most modern animals. But trilobites were the gentle ones. Anomalocaris prowled the Cambrian seas like a 6-foot nightmare with grasping arms lined with spines. Its circular mouth was ringed with razor-sharp teeth that could crack through the hardest shells. When paleontologists first discovered its fossils, they were so bizarre that scientists classified different parts of its body as separate species. The arms as sea cucumbers, the mouth as a jellyfish, the body as a sponge. They couldn't believe one creature could be so alien. Hallucigenia walked the ocean floor on 7 pairs of spines, its back covered with defensive spikes that made porcupines look cuddly. For decades, scientists couldn't figure out which end was the head and which was the tail. When they finally got it right, they realized they'd been reconstructing it upside down for 50 years. The Burgess Shale in Canada preserves these Cambrian monsters in exquisite detail. Soft tissues, delicate appendages, even the contents of their stomachs, all frozen in time like photographs from an alien world. And what those photographs reveal is terrifying. The Cambrian explosion wasn't just about new species, it was about new ways to kill. For the first time in Earth's history, animals were actively hunting other animals. Eyes evolved independently at least 20 times during the Cambrian period. Claws, teeth, armor, poison. Every weapon in nature's arsenal was invented during this biological arms race. But the real revolution was happening in the water itself.
Oxygen levels had finally reached concentrations that could support large, active animals. The ozone layer was thick enough to block most of the sun's deadly ultraviolet radiation. For the first time since Earth's formation, the surface of the planet was becoming truly habitable. And life was ready to claim it. The first plants to colonize land weren't much to look at. Simple green mats that looked more like pond scum than the mighty forests that would follow. But these humble pioneers were performing one of the most important conquests in Earth's history. Before plants, the continents were sterile wastelands of naked rock, no soil, no protection from erosion, no buffer against temperature extremes. The land was beautiful in its own harsh way, vast deserts of red sandstone carved by rivers that ran red with iron oxide, mountain ranges that gleamed like metal under the alien sky. But it was empty, silent, except for the howl of wind across barren peaks and the crash of waves against lifeless shores. The first land plants changed everything. They didn't just survive on dry land, they created the very concept of soil. Their roots broke down rock into mineral particles. Their dead bodies rotted into organic matter that could retain water and nutrients. Within a few million years, green carpets of moss and primitive ferns were spreading across the continents like a slow-motion explosion. By 400 million years ago, the first forests were rising from what had been desert just 20 million years earlier. These weren't the oak and maple forests you might walk through today. These were alien woodlands, dominated by towering club mosses and primitive conifers that grew in perfect geometrical spirals. Some of these early trees reached heights of 100 feet, but they had a fatal flaw: no real bark. Their trunks were essentially giant stems filled with water and nutrients. When they died, they didn't decay normally. Instead, they fell into swampy water where bacteria couldn't break them down efficiently. Layer upon layer of undecayed plant matter accumulated in these ancient swamps. Over millions of years, the weight of overlying sediments compressed this organic material into something that would power human civilization 300 million years later. Coal. The Carboniferous period, named for the carbon-rich coal beds it left behind, was a greenhouse world unlike anything in modern experience. Atmospheric carbon dioxide levels were 5 times higher than today. There were no polarized caps. Palm trees grew in Alaska. The climate was so warm and humid that giant dragonflies with 2-foot wingspans hunted through steaming forests where ferns grew as tall as modern oak trees. Oxygen levels reached 35%, nearly twice modern concentrations. The extra oxygen supercharged metabolism in ways that seem almost magical today. Insects grew to enormous sizes because their primitive breeding systems could finally support large bodies. Millipedes 8 feet long crawled through the forest undergrowth. Spiders, the size of house cats, spun webs strong enough to catch small reptiles. But the real giants were still in the water. The first sharks appeared during this time, and they were nothing like the streamlined predators we know today. Helioprion had a lower jaw that spiraled into a buzzsaw-like whirl of teeth. Dunkleostis, technically not a shark, but a placoderm fish, grew to 30 feet long with jaws that could snap a great white shark in half. Its bite force has been estimated at 11,000 pounds per square inch, stronger than T-Rex. These marine monsters ruled oceans that were alien in their chemistry and temperature. The water was warm enough that there was no temperature difference between the poles and the equator. Ocean currents followed completely different patterns than today. Coral reefs grew in what is now the Arctic Ocean. But life wasn't content to stay in the water forever. The first amphibians hauled themselves onto land around 365 million years ago. They were clumsy at first, more like walking fish than proper land animals. Their legs were weak, their skin was thin, and they had to return to water to lay their eggs. But they had one tremendous advantage over their aquatic relatives: access to an unexploited food source. The land was crawling with insects that had no vertebrate predators. For the first amphibians, colonizing dry land was like discovering an all-you-can-eat buffet with no competition. Within 20 million years, amphibians had diversified into forms that would make modern salamanders look like timid house pets. Some grew to 15 feet long, with skulls the size of bathtubs. Others developed armor plating that made them look like walking tanks. A few became fully aquatic again, developing into crocodile-like predators that lurked in carboniferous swamps.
But amphibians had a fatal limitation. They were still tied to water for reproduction. Their eggs had no protective shells and would dry out if laid on land. This constraint kept them close to ponds, rivers, and swamps, leaving vast areas of dry land unexploited. Evolution, as always, found a solution. The first reptiles appeared around 320 million years ago, and they brought with them one of the most important innovations in the history of life: the amniotic egg. This seemingly simple invention, a tough, waterproof shell surrounding a developing embryo, liberated vertebrate life from its aquatic nursery. For the first time, backboned animals could reproduce anywhere on dry land. They could colonize deserts, mountains, and continental interiors that had been off-limits to amphibians. The shelled egg was the key that unlocked an entire planet. Early reptiles were small, lizard-like creatures that looked almost modern compared to the bizarre amphibians they were replacing. But appearances were deceiving. These humble animals carried genetic potential that would eventually produce some of the most spectacular creatures in Earth's history. By 300 million years ago, reptiles had begun to diverge into the major lineages that would dominate the planet for the next 250 million years. Some developed specialized teeth for crushing plant material, the first herbivorous vertebrates. Others grew larger and more powerful, becoming the top predators in terrestrial ecosystems. But the most important split was happening at the genetic level, invisible to anyone watching, but crucial for the future of life on Earth. The reptile family tree was branching into 2 great divisions: one branch that would eventually lead to mammals, and another that would produce dinosaurs, crocodiles, and birds. The stage was being set for the greatest evolutionary spectacle in Earth's history. But first, life would have to survive the most devastating extinction event the planet had ever seen. A catastrophe so severe that it would wipe out 96% of all marine species and 70% of land vertebrates. The Permian extinction was approaching, and it would test whether complex life could survive the planet's own capacity for destruction. The survivors would inherit a world stripped bare, ready for evolutionary experimentation on a scale that would make the Cambrian explosion look like a gentle rehearsal. The age of reptiles was about to begin, and the greatest reptiles of all, the dinosaurs, were waiting in the wings. Think about it. You've just traveled through lost worlds and forgotten ages with me. Don't close this chapter without leaving your mark. Smash that like, hit subscribe to this channel, and ring the bell. If you don't, you're letting the story drift away into silence. And we've seen enough of that in history, haven't we? Back to our story. 252 million years ago, the world ended. Not from an asteroid, not from a volcanic eruption, from something far more insidious, the planet's own success at creating life. For millions of years, vast coal swamps had been pulling carbon dioxide out of the atmosphere and burying it underground. Ocean levels dropped, climates cooled, ice caps formed at the poles for the first time in 100 million years. The lush carboniferous greenhouse was collapsing into a frozen wasteland. But that was just the opening act. In what is now Siberia, something unprecedented was happening beneath the Earth's crust. A mantle plume, a column of superheated rock from deep in the planet's core, was rising toward the surface like a slow-motion nuclear bomb. When it finally breached the crust, it didn't create a single volcano. It created hell on Earth. The Siberian Traps eruption was the largest volcanic event in recorded geological history. For 2 million years, lava poured out of the Earth in quantities that would cover the entire United States in molten rock 3 feet deep. But the lava was the least of the problems. The real killer was the gas. Every ton of lava released clouds of sulfur dioxide, hydrogen sulfide, and carbon dioxide. The sulfur compounds created acid rain so corrosive it dissolved limestone mountains. The carbon dioxide turned the atmosphere into a greenhouse furnace that raised global temperatures by 10 degrees Celsius. But the worst poison came from an unexpected source: the coal beds themselves. As the lava flows spread across Siberia, they encountered and ignited the very coal deposits that had been forming for millions of years. Entire continents' worth of stored carbon went up in flames, releasing not just carbon dioxide, but clouds of toxic compounds that had never existed in the atmosphere before.
The oceans turned acidic. The air became unbreathable. Temperatures soared beyond the tolerance of most complex life. In less than 100,000 years, an instant in geological time, 96% of all marine species and 70% of land vertebrates went extinct. The Great Dying, as paleontologists call it, came closer to ending complex life on Earth than any event before or since. For millions of years afterward, ecosystems remained desperately simple. Just a few hardy species eking out survival in a poisoned world. But life is stubborn, and in the aftermath of the worst extinction in Earth's history, something remarkable began to happen. The survivors weren't random. They shared certain characteristics that had allowed them to endure conditions that killed nearly everything else. They were small, which meant they needed fewer resources. They were adaptable, able to switch food sources and habitats as conditions changed, and many of them had developed something new, more efficient metabolisms that could extract maximum energy from limited food. Among these survivors was a group of reptiles that would change the world: the archosaurs. Archosaurs, the ruling reptiles, didn't look like much in the early Triassic period. Most were crocodile-sized predators with long snouts and powerful legs, but they had several advantages over their competitors. Their hearts were more efficient at pumping blood, their lungs were better at extracting oxygen from air,
Their legs were positioned directly underneath their bodies instead of sprawling out to the sides, making them faster and more agile. Most importantly, they were smart. Early archosaurs had larger brains relative to their body size than most other reptiles. This extra neural power allowed them to develop complex behaviors, cooperative hunting, territorial displays, sophisticated parental care. In a world where resources were scarce, intelligence was the ultimate survival tool. By 230 million years ago, archosaurs had begun to diversify into forms that would dominate the planet for the next 165 million years. Some remained semi-aquatic, evolving into the crocodilians that still lurk in rivers today. Others took to the air, developing wings and becoming the first pterosaurs. But the most successful branch did something unprecedented in vertebrate evolution. They stood up. The first dinosaurs appeared around 225 million years ago, and they were nothing like the towering monsters of popular imagination. Eoraptor was about the size of a large dog, with long legs built for speed and grasping hands equipped with sharp claws. It looked more like a feathered lizard than the king of beasts. But dinosaurs had a secret weapon that would make them the most successful land animals in Earth's history. They were warm-blooded, or at least partially warm-blooded. The exact nature of dinosaur metabolism is still debated, but the evidence is mounting that most dinosaurs could regulate their own body temperature far better than modern reptiles. This gave them tremendous advantages in a world where climates were becoming increasingly unstable. While cold-blooded reptiles had to bask in the sun to warm up and seek shade to cool down, dinosaurs could remain active regardless of temperature. They could hunt at night, they could live in cooler climates, they could sustain high levels of activity for extended periods. By 200 million years ago, dinosaurs were spreading across the globe like a biological wildfire. The late Triassic world they inherited was a strange place, a single massive supercontinent called Pangaea, surrounded by a single massive ocean called Panthalassa. Imagine a landmass stretching from pole to pole, so vast that its interior was 1,000 miles from the nearest ocean. No maritime climate to moderate temperatures, no mountain ranges to create weather patterns, just endless expanses of desert broken by occasional oases where rivers brought water from distant highlands. It was in this harsh environment that dinosaurs first proved their supremacy. While other reptiles hugged the coasts and river valleys, dinosaurs pushed into the continental interior. They developed new survival strategies. Some became massive to conserve water and maintain stable body temperatures. Others became swift to travel quickly between water sources. But the real transformation was yet to come. Around 180 million years ago, Pangaea began to break apart. The supercontinent that had dominated Earth's geography for 100 million years started splitting along massive rift valleys that would eventually become the Atlantic Ocean. Magma welled up from the mantle, creating new oceanic crust and pushing the continental fragments apart at a rate of about an inch per year.
The breakup of Pangaea changed everything. As the continents separated, new ocean basins formed between them. These oceans created more maritime climates, with higher humidity and more stable temperatures. Sea levels rose, flooding low-lying areas and creating shallow seas that teemed with marine life. The Jurassic period had begun, the golden age of dinosaurs. The Jurassic world was a greenhouse paradise unlike anything in modern experience. There were no polar ice caps. Palm trees grew in Alaska and Antarctica. Average global temperatures were about 10 degrees Celsius warmer than today. The atmosphere contained 3 to 4 times as much carbon dioxide as the present, creating a supercharged greenhouse effect that kept the planet warm from pole to pole. But the real miracle was the rain.
Higher temperatures meant more evaporation from the expanded oceans. More evaporation meant more clouds, more precipitation, more rivers and lakes and swamps. The continental interiors that had been deserts during the Triassic became lush, humid landscapes covered in forests unlike any that exist today. These weren't the familiar forests of oaks and maples and pines that cover temperate regions today. Flowering plants hadn't evolved yet. Instead, Jurassic forests were dominated by conifers, relatives of modern pines and firs that grew to enormous sizes in the warm, humid climate. Some reached heights of 200 feet, creating cathedral-like spaces beneath their canopies. But the real giants weren't the trees. They were the animals that ate them. Sauropods, the long-necked dinosaurs, represented one of evolution's most audacious experiments. Some species reached lengths of over 100 feet and weights exceeding 80 tons. Their necks alone could be 30 feet long, allowing them to browse on vegetation 50 feet above the ground without moving their massive bodies. These weren't lumbering, cold-blooded giants struggling to support their own weight. Recent research suggests that sauropods were active, warm-blooded animals with sophisticated social behaviors. They traveled in herds, cared for their young, and may have been capable of surprisingly fast movement when necessary. Brachiosaurus stood 40 feet tall at the shoulder, taller than a 4-story building. Its heart had to pump blood up that massive neck to a brain positioned 30 feet above its body. The engineering challenges were immense, but evolution found solutions that still amaze physiologists today. Diplodocus stretched over 90 feet from nose to tail tip, but most of that length was neck and tail. Its body was surprisingly slender for such a massive animal, and its tail was equipped with a whip-like tip that could crack like thunder when flicked at high speed, possibly a defense mechanism against predators. Because the Jurassic had predators that could threaten even the largest herbivores. Allosaurus was the apex predator of its time, a 28-foot-long killing machine equipped with serrated teeth the size of railroad spikes and claws that could disembowel a sauropod with a single swipe. Unlike the massively built tyrannosaurs that would dominate later periods, Allosaurus was built for speed and agility. It could probably run at 25 miles per hour, despite weighing as much as an elephant. But Allosaurus wasn't the only threat stalking Jurassic forests. Ceratosaurus carried a prominent horn on its snout and was probably an ambush predator that lurked near water sources. Megalosaurus, the first dinosaur ever scientifically described, was a powerfully built hunter that may have been capable of taking down prey much larger than itself. The herbivores weren't defenseless. Stegosaurus carried a double row of diamond-shaped plates along its back and a tail armed with 4 sharp spikes that paleontologists call a thagomizer. Recent studies suggest the plates may have been used for display and temperature regulation, while the tail spikes were clearly weapons capable of inflicting mortal wounds on attacking predators. But perhaps the most remarkable aspect of Jurassic ecosystems wasn't their size, it was their complexity. These weren't simple predator-prey relationships. Jurassic forests hosted intricate food webs involving dozens of species of dinosaurs, plus mammals, crocodilians, pterosaurs, marine reptiles, and countless invertebrates. Different sauropod species had different feeding strategies, browsing at different heights and preferring different types of vegetation. Various predators specialized in hunting different prey animals using different tactics. The skies above these ancient forests were ruled by pterosaurs, flying reptiles that ranged from sparrow-sized insect catchers to massive soaring giants with wingspans exceeding 30 feet.
Some pterosaurs had elaborate crests that may have been used for display or species recognition. Others had teeth specialized for catching fish or filtering small marine organisms from seawater. In the oceans, marine reptiles had diversified into forms that paralleled modern whales and dolphins. Ichthyosaurs were dolphin-shaped predators with the largest eyes of any known vertebrate. Some specimens have eyeballs over 10 inches in diameter, allowing them to hunt in the depths of ancient seas. Plesiosaurs were long-necked marine reptiles that may have used their flexible necks like fishing lines, striking at prey with lightning-fast movements. But for all its biological richness, the Jurassic world was living on borrowed time. Deep beneath the Earth's surface, the same forces that had created this paradise were building toward another catastrophe. The breakup of Pangaea was accelerating. Volcanic activity was increasing. Climate patterns were becoming less stable. Most ominously, a large asteroid was wandering through the inner solar system on a collision course with Earth. In 66 million years, this cosmic bullet would bring the age of reptiles to a violent end. But that impact was still far in the future. For now, in the warm forests of the Jurassic, life had achieved a complexity and grandeur that would never be equaled. Giant reptiles ruled land, sea, and air. The continents bloomed with alien forests. The climate was stable and benevolent. It was the last time in Earth's history that reptiles would completely dominate the planet. The mammals were waiting in the wings. It was just another Tuesday morning, 66 million years ago. A massive triceratops munched on flowering plants in what would one day be Montana. Somewhere in ancient Texas, a pack of Tyrannosaurus stalked through steaming forests. Pterosaurs with 40-foot wingspans soared over tropical seas where no ice had formed for 100 million years. None of them saw the mountain-sized rock hurtling toward Earth at 45,000 miles per hour. The asteroid, 6 miles wide and denser than steel, had been wandering through space for billions of years. A leftover fragment from the solar system's violent birth, it had drifted through the asteroid belt, past Mars, beyond the gravitational pull of any planet large enough to capture it. Until now. At 11:47 a.m. on a day that would divide Earth's history forever, the Chicxulub impactor struck the shallow seas off what is now Mexico's Yucatan Peninsula. The collision released energy equivalent to 5 billion atomic bombs detonating simultaneously. The flash of impact could be seen from Mars. In the first millisecond, the asteroid vaporized completely. 6 miles of solid rock simply ceased to exist, converted instantly into a ball of plasma hotter than the surface of the sun. The ocean floor beneath the impact site, limestone bedrock laid down over millions of years, also vaporized, sending billions of tons of sulfur compounds into the atmosphere. The shockwave that followed moved through solid rock at 25,000 miles per hour. Imagine the entire North American continent jolting sideways in less than a second. In Montana, 2,000 miles from ground zero, the Triceratops never felt the plants it was chewing hit the ground. The earthquake that killed it measured magnitude 13 on the Richter scale, 1,000 times more powerful than any earthquake in recorded human history. But the seismic waves were just the beginning. The impact excavated a crater 120 miles across and temporarily created a mountain in the center taller than Mount Everest. This peak collapsed within minutes, but the debris it threw into the sky reached the edge of space before falling back to Earth as a rain of molten glass beads. These spherules, each one a tiny droplet of rock melted by the impact, spread across the entire planet like deadly hail. The sky literally caught fire as billions of these glowing fragments re-entered the atmosphere simultaneously, heating the air to oven temperatures and igniting every forest on Earth. Within 6 hours of impact, the planet was a crematorium. But that was still just the opening act. The real killer was what came next: nuclear winter on a planetary scale. The impact had lofted so much debris into the upper atmosphere that sunlight couldn't reach the surface. Temperatures plummeted from subtropical warmth to below freezing in a matter of weeks. Photosynthesis stopped. Without sunlight, plants began to die within days. Without plants, herbivorous dinosaurs began starving within weeks. Without predators, dinosaurs began dying within months. The food chains that had sustained complex ecosystems for 165 million years collapsed like dominoes.
In the oceans, the situation was even worse. The sulfur compounds from the vaporized limestone had created acid rain so corrosive it lowered ocean pH by entire units. Marine ecosystems that had flourished since the Triassic dissolved in their own toxic soup. The ammonites, spiral-shelled marine predators that had survived every previous extinction event, finally met their match. After 300 million years of evolutionary success, they vanished completely. The giant marine reptiles that had ruled the seas since the Jurassic, plesiosaurs, mosasaurs, massive sea turtles, all disappeared. On land, the statistics were even more grim. Every land animal larger than 25 kilograms went extinct. The age of giants was over. But extinction events, for all their horror, are also opportunities. The survivors didn't just endure the catastrophe, they inherited an empty world ripe for colonization. And the survivors of the KPG extinction had some surprising advantages. The first were the birds. Birds are dinosaurs, the only dinosaurs that survived the impact. But they weren't just any dinosaurs. They were small, warm-blooded, capable of flight, and equipped with beaks instead of teeth. These traits proved crucial in the post-impact world. Small size meant lower food requirements. Warm blood meant they could remain active in the cooling climate. Flight meant they could travel vast distances to find surviving food sources. And beaks, unlike teeth, were perfect for eating seeds. Seeds were the salvation of the post-impact world. While adult plants died in the darkness and cold, their seeds lay dormant in the soil, waiting for better conditions. When sunlight finally returned after months of nuclear winter, these seeds sprouted in the empty landscapes, creating the first post-impact ecosystems. The birds that survived were primarily seed-eaters, and they exploded into empty ecological niches with the speed of an evolutionary freight train. Within 1 million years, an instant in geological time, birds had diversified into forms that included some of the largest predators on the planet. Gasternus stood 8 feet tall and weighed 400 pounds. Its massive beak could crack bones like toothpicks. For 10 million years after the impact, giant flightless birds ruled the continents as the apex predators in ecosystems still recovering from the Great Dying. But birds weren't the only survivors with evolutionary potential. Hidden in burrows and trees during the impact were small, warm-blooded creatures that most dinosaurs had barely noticed, the mammals. For 165 million years, mammals had lived in the shadows of the reptilian giants, most of them no larger than rats. The largest pre-impact mammal was about the size of a badger. The impact changed everything. With the giant reptiles gone, mammals suddenly had access to ecological niches that had been off-limits for over 100 million years. They could grow large, they could become predators, they could diversify into forms that would have been impossible in a world dominated by dinosaurs. The evolutionary explosion that followed was breathtaking in its speed and scope. Within 10 million years of the impact, mammals had produced giants that rivaled the smaller dinosaurs. Eunatherium was the size of a rhinoceros, with 6 horn-like projections on its skull and saber teeth that could shear through the toughest plant material. Coryphodon weighed as much as a small elephant and was probably the first mammalian megaherbivore. But these early giants were just crude experiments compared to what was coming. By 50 million years after the impact, mammals had conquered every habitat on Earth. Some had returned to the oceans, evolving into the first whales. Others had taken to the air as bats, the only mammals ever to achieve powered flight.
Still others had grown to enormous size. Andrew's arcus was a wolf-like predator the size of a grizzly bear, with jaws powerful enough to crack the bones of early horses. The climate was helping drive this diversification. The early Cenozoic was even warmer than the Mesozoic had been. Palm trees grew in Alaska and Antarctica. There was so much moisture in the atmosphere that it rained in the Sahara Desert. Crocodiles basked in the Arctic Ocean. This hothouse world, called the Paleocene-Eocene thermal maximum, reached its peak about 56 million years ago when global temperatures spiked by an additional 8 degrees Celsius in just 20,000 years. The cause was probably a massive release of methane from ocean sediments, creating a runaway greenhouse effect that made the already warm planet nearly uninhabitable. But mammals adapted. They always adapt. Some grew larger to cope with the heat. Larger bodies are better at regulating temperature. Others became smaller and more efficient. Many took to the water during the hottest parts of the day. The early horses were no bigger than house cats and lived in tropical forests, browsing on soft leaves like tiny deer.
As the climate gradually cooled over the following 20 million years, mammals continued to evolve and diversify. Grasslands began to replace forests in many areas, creating new opportunities for animals adapted to open environments. The first true horses appeared, with longer legs for running and specialized teeth for eating grass. Predators grew larger to hunt the expanding herds of herbivores. Saber-toothed cats appeared in multiple lineages, not just the famous Smilodon, but dozens of species that independently evolved enlarged canine teeth for killing large prey. But perhaps the most significant mammalian development was happening in the trees. Around 55 million years ago, small arboreal mammals began developing traits that would eventually lead to something unprecedented in Earth's history: true intelligence. These early primates had forward-facing eyes for better depth perception, grasping hands for manipulating objects, and larger brains relative to their body size. For millions of years, primates remained small, tree-dwelling creatures that most other animals barely noticed. But they were developing capabilities that would eventually change the world: problem-solving, tool use, complex social behaviors, and most importantly, the ability to learn from experience and pass knowledge to their offspring through teaching rather than just instinct. By 2 million years ago, one particular lineage of primates had pushed these capabilities further than any animal in Earth's history. They had learned to make tools, control fire, and hunt cooperatively in organized groups. They had developed complex language and sophisticated social structures. And most remarkably, they had begun to ask questions about their own existence and their place in the vast cosmos that had created them. The age of mammals was about to become something else entirely: the age of intelligence. But intelligence, as it turned out, was a double-edged sword. The same capabilities that allowed these remarkable primates to survive the ice ages also gave them the power to reshape the entire planet. The question was, would they be wise enough to use that power responsibly? 200,000 years ago, in the heart of Africa, something unprecedented happened. A small group of primates developed a new survival strategy that would prove more powerful than fangs, claws, or armor, more effective than size, speed, or venom, more transformative than any evolutionary adaptation in Earth's 4.5 billion year history. They began to think about thinking. These early humans weren't impressive physical specimens. They stood barely 5 feet tall. Their teeth were flat and weak. They had no natural weapons, no thick hide, no impressive speed. A single lion could kill a dozen of them. Most large herbivores could outrun them. Even chimpanzees were stronger pound for pound. But inside their skulls, something revolutionary was happening.
The human brain had tripled in size over just 2 million years, the fastest evolutionary change ever recorded in such a complex organ. This wasn't just more neurons. This was a complete reorganization of how intelligence itself worked. Previous animals could learn from experience. Humans could imagine experiences that had never happened. Previous animals could recognize patterns in their environment. Humans could recognize patterns in their own thoughts. Previous animals could communicate about things they could see. Humans could communicate about things that existed only in their minds. They had discovered abstract thinking. The implications were staggering. For the first time in Earth's history, a species could adapt to environmental challenges not by evolving new genes, but by evolving new ideas. They could survive climate changes not by growing thicker fur, but by inventing clothing. They could compete with faster predators not by becoming faster themselves, but by inventing weapons that made speed irrelevant. And they could do all of this within a single generation. Around 70,000 years ago, a small group of these remarkable primates left Africa and began spreading across the globe. They crossed deserts that had stopped every previous migration. They survived ice ages that had wiped out countless other species. They reached Australia by building the first ocean-going vessels in history. They populated the Arctic by inventing technologies that allowed them to extract heat from frozen landscapes. Everywhere they went, the local ecosystem changed dramatically. In Australia, giant marsupials that had dominated the continent for millions of years suddenly went extinct within a few thousand years of human arrival. Massive wombats the size of cars, predatory kangaroos with bolt-cutter teeth, flightless birds taller than ostriches, all vanished as these small, seemingly insignificant primates learned to hunt cooperatively and modify their environment with fire. The same pattern repeated across the globe. In North America, mammoths, giant ground sloths, saber-toothed cats, and cave bears disappeared shortly after human arrival. In Europe, cave lions, giant elk, and woolly rhinoceroses followed them into extinction. On isolated islands, entire ecosystems collapsed within centuries of human colonization. Some scientists call this the Quaternary extinction event, the sixth great dying in Earth's history. But unlike the previous 5 mass extinctions, this one wasn't caused by asteroids, volcanoes, or climate change. It was caused by intelligence itself. Humans had become a geological force. But the real transformation was just beginning. Around 10,000 years ago, scattered groups of humans independently discovered something that would change the planet more profoundly than the impact that killed the dinosaurs: agriculture. For 4.5 billion years, life on Earth had been limited by a simple rule. You could only eat what grew naturally in your environment. Predators were constrained by the availability of prey. Herbivores were constrained by the availability of plants. Population sizes fluctuated with natural cycles of abundance and scarcity. Agriculture shattered these ancient limitations. Humans began deliberately modifying plants and animals to increase their usefulness. They selected seeds from the largest, most nutritious wild grasses and planted them in organized fields. They captured wild animals and bred them for docility and productivity. They modified entire landscapes to maximize food production. Within just a few thousand years, they had created crops that were recognizable compared to their wild ancestors. Modern corn ears are 1,000 times larger than their wild predecessors. Wheat seeds are so modified that they can't even disperse naturally. They require human intervention to survive. Domestic cattle,
pigs and sheep are so different from their wild relatives that they're essentially new species created by human intelligence. The results were immediate and dramatic. Human populations exploded from a few million scattered hunters and gatherers to hundreds of millions of farmers living in permanent settlements. For the first time in Earth's history, a single species was deliberately reshaping the planet's biology on a continental scale. Forests that had grown wild for millions of years were cleared and replaced with geometric fields of human-selected crops. Wild animal populations were pushed aside to make room for domestic herds. Rivers were diverted to irrigate farmland. Even the composition of the atmosphere began to change as humans cleared forests and tilled soil, releasing stored carbon into the air. But agriculture was just the foundation for something even more transformative: civilization. As food production increased and human populations grew, some individuals could specialize in activities other than gathering food. They became tool makers, builders, traders, warriors, priests, and eventually thinkers who spent their entire lives trying to understand how the world worked.
These early scientists made discoveries that seem obvious now, but were revolutionary at the time. They figured out that the Earth was round, not flat. They calculated the size of the planet with remarkable accuracy using nothing but shadows and geometry. They discovered that the same laws that governed falling objects on Earth also governed the movements of planets in the sky. Most remarkably, they began to ask questions about deep time itself. Where did the Earth come from? How old was it? What were those strange spiral shells and giant bones they sometimes found embedded in solid rock? Could the world have been different in the past than it was in the present? These questions led to discoveries that revolutionized human understanding of their place in the cosmos. The Earth wasn't thousands of years old, as most people had assumed. It was millions of years old, then hundreds of millions of years, then billions. Life hadn't always been the same. Species had appeared and disappeared throughout history. The rocks themselves told stories of ancient oceans, buried forests, and climates unlike anything in human experience. Most shocking of all, humans themselves weren't separate from this deep history. They were part of it. The same evolutionary processes that had shaped dinosaurs and trilobites had also shaped human beings. The atoms in their bodies had been forged in dying stars billions of years ago. The oxygen they breathed had been produced by ancient bacteria. The food they ate grew from soil that contained the remains of countless extinct creatures. Humans weren't just observers of Earth's history, they were the latest chapter in it. But they were also something unprecedented, the first chapter with the power to consciously direct what came next. By the 18th century, human technology had become powerful enough to harness the fossilized energy of ancient forests. Coal, the compressed remains of carboniferous swamplands, began powering machines that could produce goods faster and more efficiently than any biological process. Steam engines, textile mills, and iron foundries launched the Industrial Revolution, transforming human civilization from agricultural to mechanical in less than a century. The pace of change accelerated exponentially. In 1800, the fastest humans could travel was the speed of a galloping horse, about 30 miles an hour, the same speed that had been maximum for thousands of years. By 1900, they were traveling at 100 miles an hour in steam-powered trains. By 1950, they were flying at 500 miles an hour in aircraft. By 1970, they were traveling at 25,000 miles an hour in rockets that could reach the moon. The transformation wasn't just technological, it was geological. Human activities were now moving more rock and sediment than all natural processes combined. They were changing the chemical composition of the atmosphere and oceans. They were driving species extinct at rates comparable to the great mass extinctions of the past. Some scientists argue that Earth has entered a new geological epoch, the Anthropocene, the age of humans. The evidence is overwhelming. Human activities have increased atmospheric carbon dioxide to levels not seen for 3 million years. Global temperatures are rising at rates that would have been catastrophic for most previous ecosystems. Ocean chemistry is changing as rapidly as it did during the Great Dying 252 million years ago. But unlike previous mass extinctions, this one is being driven by intelligence rather than random catastrophe. And that intelligence is beginning to understand what it's doing. Humans have developed technologies that can monitor the entire planet in real time. They can track global temperatures, measure atmospheric composition, and predict climate changes decades in advance. They can sequence the DNA of extinct species and potentially bring them back to life. They can even detect planets orbiting distant stars and speculate about whether life might exist elsewhere in the universe. Most remarkably, they can look backward through deep time and see their own place in the vast story that began with the Big Bang 13.8 billion years ago. They understand that they are made from stellar debris, evolved from ancient bacteria, and connected to every living thing that has ever existed on Earth. This perspective brings both tremendous responsibility and unprecedented opportunity. Humans now have the power to prevent mass extinctions rather than cause them. They can develop technologies that work with natural systems instead of against them. They can even begin to expand life beyond Earth itself, ensuring that the 4.5 billion-year experiment in terrestrial biology isn't limited to a single planet. The story that began with the violent birth of the universe has led through an almost incomprehensible series of accidents and adaptations to a species capable of understanding its own cosmic context and consciously directing its own evolution.
Standing here in the present moment, you are the temporary arrangement of atoms through which the universe is becoming aware of itself. The carbon in your muscles was forged in the nuclear furnaces of ancient stars. The calcium in your bones was created in supernova explosions that lit up alien skies billions of years ago. The iron in your blood was scattered across space by stellar deaths and gathered by gravitational forces into the rocky planet that became your home. Your lineage stretches back through mammals that survived the asteroid impact, through dinosaurs that ruled Jurassic forests, through amphibians that crawled from carboniferous seas, through fish that developed the first backbones, through the simple bacteria that first learned to harness sunlight and poisoned their own atmosphere with oxygen. You are the descendant of survivors. Every single one of your ancestors, stretching back billions of years, successfully reproduced before dying. You carry within your DNA the memory of Earth's entire biological history. But you are also something new under the sun, a thinking, questioning, self-aware part of the universe that can contemplate its own existence and choose what happens next. The deep history of Earth teaches us that change is the only constant. Species appear and disappear. Continents drift and collide. Climates shift from greenhouse to icehouse and back again. What survives is not what's strongest or largest or most specialized, but what's most adaptable to change. Human intelligence may be evolution's greatest experiment in adaptability. The same capabilities that allowed your species to survive ice ages and spread across the globe now give you the power to consciously guide your own future evolution and perhaps the evolution of life itself. The story that began 13.8 billion years ago with the birth of time and space has led to this moment. You, listening to these words, aware of your place in the vast cosmic story, capable of deciding what the next chapter will contain. The universe spent billions of years creating you. What will you do with this gift?
History is full of voices that were silenced because no one chose to remember. Don't let this story be another echo that fades away. Like this video, subscribe to this channel, and turn on notifications. Because if you don't, this too may vanish, just like the civilizations we talk about.